Welcome to the video lecture series of computer organization and architecture. In previous class, we have seen program control using hardwired and microprogram control. Now, in this particular lecture, we will talk about how we can optimize the working of the system, means how we can increase the performance of the system and we can take a maximum throughput or efficiency from the system. So, there are few methods through which we can handle to optimize the system in various way. So, let us talk about one of the best method, that is pipelining, in this particular lecture. So, in case of pipelining, the system is divided into various type of segment, and through pipeline we can organize the system in such a way that separate segments are working on different tasks or different operations, they are performing different operations. So, pipelining is the technique through which we can increase the system performance, or we can get maximum efficiency from the system, and the performance will automatically increase. So, to do this, the concept of parallelism will come in picture, that is the part of computer architecture. Here we will talk about only one particular concept of pipelining in computer organization. So, to study detail of parallel architecture, you can refer the computer architecture book by Kai Hong. That is the best book for advanced computer architecture, from where you can get the idea of parallel computer structure. So, pipelining is the basic concept of handling the system in such a way that parallelism can be maintained in such a way that maximum throughput can be achieved, or system is working in different tasks on different tasks in parallel way. So, this is the basic background of pipelining, where we are going to study what type of architecture is there in pipelining and what type of pipelines are available. So, there are basically two pipelines that we will discuss or cover in this particular lecture, that is linear pipeline computer system and nonlinear pipeline system. In general, the pipelining is very simple, like a water pipe, where if we cut the water pipe in different segments, and different segments are working in different on different tasks, and they are performing different operations, and all the segments are working in parallel, so that maximum output can be achieved. Let us have one example, simple example of pipelining. Here you can see, to execute any instruction for the same instruction like add R1 R3, simple instruction, you can see here the instruction has to be executed by the pipeline or non pipeline system. So, what is the difference between these two architecture? So, if it is a pipeline, so obviously the instruction cycle has to be maintained. So, what is the common or general instruction cycle? That is, instruction fetch step has to be executed, then instruction decoding will be performed, and if operand is required, that operand is to be fetched from main memory. So, operand fetch, which is an optional step, is required, and finally, the instruction execution will take place. So, if these four steps are important to execute particular instruction like add R1 R3. So, here you can see this is an instruction, and this has to be fetched from main memory, because all instruction or program is stored in main memory. So, the processor or the system needs to fetch the instruction from main memory. So, that is why instruction fetch operation will be performed, and then this instruction will be decoded by the instruction decoder, and accordingly various control signals are issued, that we have seen in last class also, how control signals are issued in what step, or what should be the sequence of generating the control signal. So, in this particular instruction example, the second operand is stored in main memory, and the address is given in R3. Obviously, the third step is also required, because second operand is stored in main memory, it is not given in R3. So, operand fetch step will also be performed in this particular case, and when the second operand is available and the instruction is already decoded, then only the instruction execution will take place, execution of R1 plus MDR out data. Why MDR? Because the second operand we have fetched from main memory and it is available with MDR. So, that is why MDR we have written, the second operand is available with MDR. So, in ALU the add operation will be performed, the execution means addition operation, addition of two operand which is performed in the ALU. So, this way the instruction will be executed. Now, if it is a pipeline system, then we can convert the whole system, or we can divide the whole system in different segments, and each segment will perform different tasks. These are denoted by S1, S2, S3 and S4. These are different segments, and the first segment is performing instruction fetch operation, IF, denoted by IF, and the second segment can perform instruction decoding operation, and the third segment will perform operand fetch, and the fourth segment will perform the execution, and after execution this pipeline system will produce some output, that is addition of R1 plus R3. So, this way the whole system is divided into different segments. In first case, when the first instruction comes to execute, or first instruction is going to be executed by the system. So, this segment will work in first case and other segments are empty, other segments are empty. So, only one segment is working, and after fetching of first instruction, this instruction will be given to the second segment, that is S2 or instruction decoding, where the first instruction which was fetched in first case or first segment has to be decoded here in second, and this segment will be an empty. So, what we can do? So, this segment will start fetching the second instruction or next instruction. Now, these two segments are working in parallel. So, how this architecture will help on increasing the parallelism or increasing the efficiency or maximum throughput or good throughput from the system. So, if these four segments are working in parallel, then only we say the parallelism can be maintained by the system. So, first instruction has been fetched and it is given to the instruction decoder. This particular segment is decoding first instruction and the second instruction is in parallel to that has been fetched, and after decoding this instruction is given to third segment, that is operand fetch step, and this will work on second decoding of second instruction, and this segment is free. Now, this can fetch the third instruction. So, let us see in time cycle diagram in detail. This particular example we can also understand in time space diagram. Now, here you can see the stage 1 is working on first instruction. After finishing its task, this instruction will be given as output to the input of second stage, and now these two stages are working in parallel, means this tau clock cycle or this clock cycle is common. Now, after doing the task, this instruction will be given to next stage. Now, three segments are working in parallel and with the common clock cycle, and after that in fourth clock cycle you can see all the four stages are working in parallel, and after this fourth clock cycle the first output will be produced by this system, that is output of first instruction. But after first instruction you can see or you can observe every clock cycle this system will produce the output. output of I3 like that, etc. So, only in first case the pipeline system is working as non-pipeline system, but after giving or producing the output of first instruction, this will produce the outputs or corresponding outputs in every clock cycle. So, what is the difference between pipeline and non-pipeline system? You can see in case of non-pipeline system, it will not execute the next instruction until it produce the first output. So, you can see 4 clock cycles are needed to execute any instruction in case of non-pipeline system. So, we can compare both these two architecture and we can see which system is performing better or which system is giving the good output. But there was a problem in this system. So, we have to decide the clock period accordingly. So, what was the problem? We can see the instruction fetch operation may be slower because it is related with memory. So, we can see every segment may work on different clock cycle, will take different time. We cannot decide a common clock cycle for this particular system. Suppose this system is slowest one or this segment is the slowest segment. So, this will become a bottleneck for the whole system. S1 and S2 will perform their task and will wait for the S3 to finish its task, because this cannot produce its output to the S3, because S3 is working on different particular task, different tasks, and it is slower than other segments. So, that is why this particular architecture will become a bottleneck, or the drawback of this architecture is a bottleneck problem. So, to overcome this particular drawback, we introduce the latches in between of every segment. You can see here these are latches. So, whenever segment completes its task, it will produce the output, and these latches are used to hold the intermediate results. These results are stored in these latches. So, how clock cycle can be decided, or what should be the clock cycle of this particular system? The clock cycle is nothing but it is a maximum of particular segment, which is the slowest one. We have to consider the slowest one segment's time period in this case, because if this segment is slowest, this will become a bottleneck again if we are not considering the slowest segment time cycle. So, that is why it is written as maximum of tau I plus tau L. Tau L is nothing but it is a time taken by the latch to store and to fetch from the latch. So, this is the small time interval, that is tau L, that we have also to be considered in this case to decide the clock period, and clock period will T max plus T L, that you can observe. And what is the frequency of the system? That is 1 upon tau. So, let us have a comparison of speed to execute different instructions. The comparison of two systems, that is pipeline system and non-pipeline system, because commonly very common question may be asked that how will you identify that which system is faster and what is the speed up factor and how many times the system is faster. So, as I said, in case of pipeline, we are maintaining the parallelism, and if we are maintaining the parallelism, we are increasing the performance or good throughput can be achieved in this case. So, how much time the system is faster? So, we can consider a general case. There are few assumptions. There are n instructions are to be executed by the non-pipeline and pipeline system. Suppose there are n instructions are to be executed, and there are k stages of the pipeline system, means non-pipeline system is converted into k number of stages, and tau is the clock cycle that we have decided just before, and T n is the small t n is the total time taken by non pipeline system to execute any instruction. So, keep it in mind, what is T n? T n is the total time taken by the non pipeline system to execute, to finish the instruction completely. So, here you can see what is T n? T n in it is 4 in this case, it is 4 in this case, in case of non pipeline. T n is 4 clock cycles. So, what is the speed up factor that can be defined by the ratio of T 1 and T 2? What is T 1? T 1 is the time required by the non pipeline system to execute an instruction divided by time required to execute an instruction by the pipeline system. The ratio of time taken by the non pipeline and pipeline system to execute an instruction, T 1 upon T 2, capital T 1 upon capital T 2. So, what is capital T 1? So, as I said, there are n instructions and each instruction is taking T n time period. So, T 1 will be n times T n. And what about T 2? As I said, in time space diagram, in first case the pipeline system is behaving like a non pipeline system in first case only, and after that in every clock period tau the system is producing next output. So, that is why it is k tau in first case, because this non pipeline system is converted into k number of stages. So, k tau will be the time period for first instruction, k tau. First instruction will take k times tau, because the non pipeline system is converted into k number of pipeline system, or you can say k stages are given in the pipeline system. And how many instructions are remaining? N minus 1 instructions are remaining now. And after the first instruction, this system will produce the output of next instruction in every tau clock cycle. So, that is why n minus 1 times tau is given, right. So, Sk will be, the speed up factor will be simple T 1 upon T 2. So, if you calculate, it will come as n T n upon k plus n minus 1 times tau. So, this is the formula for speed up factor. We can easily calculate the speed up factor for pipeline system, or we can see the pipeline system is faster than the non pipeline system. If we consider n tends to infinity or very large, or if we consider n is very large, very large, and T n is equal to k times tau. That means the non pipeline system is converted into pipeline k stage pipeline system. So, obviously, and T n will be k times tau. So, what will be the speed up factor in that case? So, n k tau upon k plus n minus 1 times tau. So, if n is very large, so we can consider k plus n minus 1 equals to n, that is equivalent to n. So, this speed up factor in that case S k equals to n k tau upon n tau. So, this will cancel out, it will become as k. So, we can claim that the k stage pipeline system is k times faster than corresponding non pipeline system. So, we can prove the speed up factor for this case. So, this is a general question you may be asked to prove the speed up factor for pipeline system having k stages, which is k times faster than corresponding non pipeline system. So, this way you can prove. There are few more performance matrices through which we can calculate the system performance. Next is efficiency. Efficiency is nothing but the speed up factor divided by k. So, if you calculate this, this will come as n k tau upon k times k plus n minus 1 times tau, and the efficiency will be maximized when we consider infinite number of instruction. When we consider large number of instruction, we can see the efficiency is 100%. 100% efficiency will be produced by the pipeline system. And we can also calculate the throughput of the system, which is nothing but it is denoted by omega, it is equal to efficiency by clock period, that is eta upon tau. So, this will come as n upon k plus n minus 1 times tau, and if we are considering 100% efficiency, that means eta equals to 1, then omega will become as 1 upon tau, that is equivalent to frequency. So, in a single clock period, you can see the whole instruction can be executed by the system. So, maximum throughput can be achieved. This way we can consider different parameters. The next type of architecture is a non-linear pipeline system. So, in case of linear pipeline system, all these segments are producing outputs and that output will become an input for the next stage. However, in this case there are few more connections are given. This is feedback connection, means we can jump on the previous stage also. Suppose we are at the stage S3, we can jump on previous stage, that is S2. This is again a feedback connection, and there is a feed forward connection also. So, in case of non-linear pipeline system, there is a facility of feed forward and feedback. So, we can jump on previous stage. So, in programming somewhere it is required, we need to jump on previous stage, or some branch operation has to be handled. So, when branching is given, then this particular architecture is helpful. We have to jump in particular address, because in case of branching some offset value is added with the current address of the program counter. So, we have to jump, or the processor or the sequence of instruction execution will be jumped on next location, and that location will be given in some offset value. So, current PC value will be added with the offset value to get the next location of instruction, where the branch instructions are given. So, in that case non pipeline system will work. So, here that is why feed forward and feedback connections are given in this particular case, non-linear pipeline. So, it is not linear, we can see. So, what type of reservation table or what type of time space diagram we can consider here in this case. So, how this particular architecture will be helpful to improve the efficiency and throughput or the system performance. So, for dynamic programming, this particular architecture will be helpful, non-linear pipeline system. However, all the stages are working on different tasks or different operations they are performing, but it supports dynamic programming also, means there is a facility of jumping back and jumping on forward direction. So, back and forward direction jumping is also possible in this particular architecture. So, let us have an example. The first figure simply says the output is produced by some segment. So, let us see the diagram. Here you can see the S3 segment is producing the output of Y, and the S1 unit or S1 segment is producing the output of X. There are two type of different instructions we can execute parallelly through this particular system, and the output of X type of instruction can be produced by segment number 1 only, and the output of Y can be produced by the segment number 3 only. That we need to take care, and we can design different reservation tables. That is not there is no constraint of fixing this particular reservation table. So, we can design different type of reservation table. So, this is the one shot of reservation table. The first table shows the output of X, or for particular instruction X, this reservation table shows the execution of X type of instruction, and this the second one shows the reservation table for Y type of instruction. So, how this reservation table is drawn? Let us try to understand. You can see the input is given from S1 stage. So, reservation table will always start with S1 stage. So, that is why this cross or X is given in S1 stage. Now, we can move from S1 to S2, or we can move from S1 to S3 directly, it depends. So, if we are following some sequence, so obviously, we will jump on S2, then from S2 to S3. So, that is why you can see from S1 we are jumping on S2 stage, and from S2 we are jumping on S3 stage, and from S3 either we jump back to S2 or to S1, because there are feedback connections, because S3 cannot finish or cannot stop this reservation table, cannot stop the instruction execution of type X, because S3 is producing only Y type of instruction, and this reservation table, the first reservation table stands for X type of instruction. So, only S1 will produce the output of X. So, ultimately this will finish on S1. Mean in between we can jump back or forward, it depends. Suppose in this case from S3 we are jumping to S2. So, what connection we are using? From S3 to S2 we are using this type of connection, this feedback connection is used, and in next from S2 we are jumping on S3. So, that means we are using the linear connection, and after S3 again we can jump on S2 either, or we can jump on S1, and suppose in this case we are jumping from S3 to S1. So, that means we are using this feedback connection. This feedback connection is used to jump from S3 to S1. So, there is no fixed rule of jumping of one stage to another stage, where what type of connection we are using feedback, either we can use or feed forward we can use, it depends. It depends on a given condition of the program. Now, you can see from S3 we are directly jumping to S1 and we stop here. So, this reservation table stands for X type of instruction. Likewise, we can also draw the reservation table for Y type of instruction. So, these two examples we can consider to understand the non-linear type of pipeline system. However, we can also draw different reservation table for X and Y also, and this is not fixed reservation table for X, generating X or Y. So, this way we can understand the non-linear pipeline system, and we understood that how pipeline system are performing or can be used to increase the system throughput, or the performance of the system can be increased through pipeline system. So, that is all about this particular lecture. Thank you.